My name is Maayan Shvo. I'm a PhD student at the University of Toronto, and I'd like to talk to you about our work, which was presented at this year's EEI conference on interpretable sequence classification via discrete optimization, which was done in collaboration with Andrew Lee, Rodrigo, Toro, Icarte, and Sheila McIlraith. I need to operate two computers. Sequence classification is the task of predicting a class label given a sequence of observations. For example, given a sequence of credit card transactions, as can be seen here, we want to say whether or not the sequence contains fraudulent transactions. And so that's an example of binary classification, but it's often the case we have more than two class labels, and this is known as multi-class classification. For example, in a malware detection setting, given a sequence of interactions between an app and the operating system of a smartphone, we would like to be able to classify the family of malware that generated the trace. In many settings, we also care about early classification. For example, in healthcare monitoring, early detection of sepsis is crucial to prompt intervention, which can potentially be life-saving. So, instead of providing a classification given a full trace, we want to provide a prediction after every incoming observation, sepsis or no sepsis. Now, what we want is a box, a classifier that can classify unseen traces accurately. And importantly, we want to learn this classifier from potentially noisy large sets of labeled traces, as can be seen here, where each trace is coupled with a class label and where the classifier captures the patterns in these traces. Now, neural networks such as LSTMs trained with gradient-based optimization have been shown to be very powerful sequence classifiers, but the rationale for classification can often be difficult for humans to discern. In contrast, here we learn interpretable classifiers that take the form of deterministic finite state automata using discrete optimization. Our automata-based classifiers, by virtue of their connection to formal language theory, are both generators and recognizers of the pattern language describes each class in the data set. Now, one nice thing with these DFA classifier is that we can trace some sequence of observations through them and check if we end up in an accepting or rejecting state, right? Does this trace belong to this class or not? And not only that, we can also query the classifier and ask questions such as, well, I understand that the trace was rejected, but what would have caused you to accept it? What changes to the trace would have caused you, the classifier, to predict that this trace belongs to a certain class? And this is a question our classifiers can answer by generating so-called counterfactual explanations, which are alternative traces that would have been accepted by the classifier. For example, here you can see on the left a trace that would have been rejected by this particular classifier. And the trace on the right is one that would have been accepted by the classifier, with only one observation token having been modified in the trace on the left to obtain the trace on the right. And so we really get a sense of the nice properties of these DFA classifiers and the ways in which they are interpretable. They allow us to scrutinize the rationale for making a classification, and they are queryable and allow us to, for example, ask for a counterfactual explanation to understand what would have caused them to change their classification. In the paper, we discuss this in more detail, as well as other interpretability services, such as verification of classifier properties, for example, using LTL, and classifier modification. We don't have much time, but I'll just mention in a nutshell that the way to learn these DFA classifiers is by taking a large set of traces, learning one DFA per class using a MILP model. And finally, in order to provide a final classification, we consider the prediction given by each binary DFA classifier and combine them using posterior inference. Sorry about that. Yeah, so I'll mention quickly that we evaluated our approach on several synthetic and as well as noisy real world data sets and show that our classifiers have comparable test performance to LSTMs with the added advantage of being interpretable. And here's just an example of one such DFA learned from one of our data sets. And of course, a lot more details on our experiments can be found in the EEI paper and the supplementary material that went with it. And just, again, to summarize, we discussed our approach that proposes to learn DFA classifiers from large sets of label traces, and discuss also the interpretability of these classifiers, illustrated by our ability to walk through them, to generate counterfactual explanations, to verify and to modify them. Our classifiers may be learned using discrete optimization. And we talked about how, empirically speaking, they have shown performance that's comparable to LSTMs with the added advantage of being interpretable. So I invite you all to read our paper, and I thank you very much for your attention. Thank you.